In this lecture, I want to go over 3 examples from last fall's final exam. So last semester's final exam. First one is to calculate the area of the triangle with vertices 1, 3, 1, 1, 5, 4, and 2, 3, minus 1. So we're given 3 points of the triangle. And what we want to do to figure out the area of this triangle is to take vectors making use of these 3 points. So we want to use all 3 points and calculate 2 vectors from these. So I'm going to go from this point to this point first. So that'll be one of my vectors. That's the vector u. 1 minus 1 is 0. 5 minus 3 is 2. 4 minus 1 is 3. So I'm getting the vector 0, 2, 3 from going from the first point to the second point. And then again, you just want to make sure you use this point. You can go from this point to this point, or this point to this point, or just use this point for the other vector. So I'm going to go from 1, 3, 1 to 2, 3, minus 1. That's going to be 2 minus 1 is 1. 3 minus 3 is 0. And negative 1 minus 1 is negative 2. So that gives me my second vector. And what I want to do is take the cross product of these two vectors. The length of that cross product will be the area of a parallelogram that has these 3 points here as vertices of the parallelogram. So what we want to do is take the cross product of these two, and then the length of that vector will give us the area of the parallelogram. And for the area of the triangle, we want 1/2 of that. So I'm doing u cross v. You could do v cross u, but I'm doing u cross v, so I'm putting 0, 2, 3 here, 1, 0, minus 2 there. I'm going to get minus 4 minus 0, so minus 4. I'm going to get 0 minus 3. We want minus that for the j component, so that's 3. And then 0 minus 2, that'll be minus 2. So we got our vector, that's a cross product. And again, the length of this will be the area of the parallelogram, which has these 3 vertices. So 16 plus 9 plus 4, squaring these and adding, we get 29. And so the square root of 29 will be the area of that parallelogram. So the area of this triangle is 1/2 of that, 1/2 the parallelogram. So once I know that the area of the parallelogram is square root of 29, I can say the area of the triangle is the square root of 29 divided by 2. So that would be the answer to this problem. So the next problem is finding the arc length of a curve where t is between 0 and 1. We want to take the derivatives of each of these, square them, and add them. And then what we want to integrate is the square root of that. So I take the derivative of t cubed minus 6t. I'm going to get 3t squared minus 6. And again, I want to square that derivative. And then I take the derivative of this, which is just 6t, and square it. Take the derivative of this, which is 6t, and square it. And then I want to add these. So when you square this, you're going to get 9t to the 4th minus the middle term, which will be twice the product of these two. So minus 36t squared, and then plus 36. And let me clarify, I get 9t to the 4th from this. The middle term again is minus 36t squared, but I have a 36t squared here that's going to cancel with that, and another 36t squared here, which gives me a 36t squared. So the t squareds are going to end up just being 36 of them. And then we have plus 36 from squaring this. And so this will be what we get when we expand this. So now we want to try to write this as a square because we know we have to integrate the square root of this. So hopefully it's something nice. Now you could take out a 9 first here, that might help. But really the square root of this is 3t squared, and the square root of this is 6. So you can sort of see that if this is going to be a square, it has to be 3t squared plus 6 squared. We get the 9t to the 4th, we get the 36. The middle term is in fact twice the product of these, so it is 36t squared. And so this is the right equation here. And so we want to take the square root of that. So we're just going to have 3t squared plus 6. And we want to integrate that from t equals 0 to 1. So this is how we're going to get the arc length. We integrate 3t squared, we get t cubed. We integrate 6, we get 6t. So we're getting t cubed plus 6t. And we want to evaluate this from t equals 0 to 1. At 1, we get 7. And at 0, we get 0. So we're just going to end up with 7 for our answer. So the arc length then is 7. And that finishes the second example. And the last example I want to do from the fall 2019 final exam is this question. And this one is a little bit tougher. You're given two planes, P1 and P2, that are parallel to this plane, and they are tangent to the surface. And you want to know the distance between those two planes. So what are we going to do with this? Well, first, remember how we get tangent planes to surfaces. We bring everything on one side, so I'm going to bring the z over. And I'm going to call this capital F. So this expression minus z. And I want to take the gradient of capital F. And that gradient will be normal to the tangent plane at the point xyz, where xyz is a point on the surface. So let's go ahead and take that gradient. We take the derivative of this with respect to x. We're going to get 2xy minus 2y plus 2. Take the derivative of this with respect to y. We're going to get x squared minus 2x minus 1. And the derivative with respect to z is just going to be negative 1. So this is the gradient. And again, if I'm at a point xyz on this surface, this gradient is normal to the tangent plane. What do we know about the normal to the tangent planes that we want? Well, these planes are parallel to this. They're parallel to each other, and they're parallel to this. And that's going to mean that the normals are all going in the same or opposite direction. So we can see that 3, 4, minus 2 is normal to this plane, so it's going to have to be normal to both of these since these three were parallel. And that means that the normal we get from using the gradient has to either be going in the same direction as 3, 4, minus 2 or the opposite direction. And so it has to be a multiple of 3, 4, minus 2. So this is going to equal some number k times 3, 4, minus 2. So we want to know what that means now. And you can see that minus 1 is equal to k times minus 2. So that tells you that k has to be 1/2, right? 1/2 times negative 2 will give me the negative 1. So we're getting then that k is 1/2. Now, how can we use that? Well, we can see then that x squared minus 2x minus 1 has to equal 1/2 times 4, or 2. So x squared minus 2x minus 1 equals 2 means that x squared minus 2x minus 3 equals 0. And here I've factored this expression that's equal to 0. It's x minus 3 times x plus 1. We get a minus 3x and plus 1x is minus 2x. And then minus 3 for the constant and x squared for the leading term. So we get this factorization, and this tells us that x has to equal 3 or negative 1 if this vector here, this gradient, is going to be parallel to this normal we got from this plane up here. So we need then for x to be 3 or negative 1. I'm going to look at each of those possibilities. And then I'm going to use the last remaining equation from here, that this first component has to equal 1/2 times 3 to figure out what y is. So when x equals 3, we're going to have 6y minus 2y, which is 4y, plus 2 is equal to 1/2 times 3, 3/2. So again, when x equals 3, that's one of the possibilities for x. We're going to get 4y plus 2 is equal to 3/2. Subtracting 2, we get a negative 1/2 on this side, and dividing by 4, we get y is negative 1/8. When x is negative 1, we're going to have negative 2y minus 2y. That's negative 4y plus 2 is again 3/2. we take the 2 on the other side. 3 halves minus 2 is negative 1/2. Divide by negative 4, we get y is 1/8. So y is 1/8 now. And now we know x and y is either 3 minus 1/8 or minus 1 1/8. We still need the z component. But what we have is that x is 3 and y is negative 1/8 and z is something. And the other point is negative 1 1/8 and z is something. So how do we figure out what the z is for these points? Well, remember, we're looking for points on the surface. So what we got to do is go ahead and plug in 3 and minus 1/8 into here to figure out what z is. So we have 9 times the negative 1/8. That'll be minus 9/8. Then we're going to have a minus 2 times 3 times the negative 1/8. That'll be plus 6/8. So minus 9/8 plus 6/8 is negative 3/8. Here I'll have another plus 1/8 since y was negative 1/8. So I have negative 3/8 plus 1/8 is negative 2/8 or negative 1/4. And then I'm adding 6 to that, 2 times 3. So 6 minus 1/4 is going to give you 23/4. That's going to give me this. And so I get the z component that way. I won't go through the arithmetic for this one, but again, you just replace x with negative 1 and y with 1/8, and you will end up with z being minus 7/4. So that gives us these 2 points, and these are the points on the surface where the tangent planes are parallel to this plane. So let's say P1 corresponds to this one and P2 corresponds to this one. So P1 is tangent to the surface at this point, and P2 is tangent to the surface at this point. And they're both parallel to this plane. So what do we do now? Well, it's tempting to write down the equations for P1 and P2, but that's actually not really what you want to do. I mean, it couldn't hurt, but it's not really the goal here. The goal is to find the distance between these two planes. And just for example, why we wouldn't even need the equation for P2 is we know this point on this plane, P2. And so since P1 and P2 are parallel planes, they're parallel to this plane, so they're parallel to each other. If I know a point on P2, then all I really want to know is the distance from that point to P1. Right? The distance from a point on P2 to the plane P1 will be the same for every point on P2 because the two planes are parallel. So I want to find the distance from this point to the plane P1. But we really don't even need to know the equation for plane P1. So why is that? Well, what's the goal here? We want to find the distance from this point now to the plane P1. So let me draw a picture here that we used before. This point is the point corresponding to this point on P2. And Q will be this point here on the plane that we want, this plane P1. We're trying to find the distance from the point on P2 to the plane P1. So we want to know this distance. And again, the idea from before was to take this vector from Q to P and project it onto the normal vector to the plane P1. And the length of that projection will be the distance then from the point on plane P2 to the plane P1. So to get that, all we need is this point then on the plane P1, and we need a normal to the plane P1. You might think you need the equation for the plane P1 for that normal, but you don't, because P1 was parallel to this plane. So the normal to this plane, 3, 4 minus 2, has to be parallel to the normal to this plane, but that's going to mean it's normal to this plane. So if I take my normal 3, 4 minus 2 to this plane, it's also normal to this plane because they're parallel. So if this is perpendicular to this plane, it's going to be perpendicular to this plane. So I can use this as my normal to my plane P1. I have a point on my plane P1, and I have a point on my plane P2 that I'm using for the P0 in this picture. So I'm going to take the vector going from this point to this point. That's -4. Then I have 1/8 minus a -1/8 will give me 2/8 or 1/4. And then -7/4 minus 23/4 is -30/4 or -15/2. So that's giving me the vector in this picture going from Q to P0, Q to P. Okay, so that's the Q to P0 in this picture. Now I want to go ahead and project that onto the normal, project it onto N here. And I want that length. We want the length of that projection. And to remind you, that means I take the absolute value of the dot product of these two vectors, QP and N, and I divide by the length of the vector N, the vector you're projecting onto. So what is a dot product of QP and N? It's -12 plus 1 plus 15. So it's -12 plus 16, or 4. And I want to divide that by the length of the vector N. The length of the vector N is, we have 9 plus 16 plus 4 here. That's going to be 29. You want the square root of that for the length of N. So the answer is going to be 4 over the square root of 29. That will be the distance then that we want from this point to the plane P1, which will be the distance then between the two planes.